Imagine for a moment that you are standing in a quiet room. In the palm of your hand, you hold a tiny, fragile box. Inside is a single particle of light, a photon. Now, imagine your friend is standing in a room just like this one, but their room is not across the street or even on the other side of the planet. Their room is in a space station orbiting Proxima Centauri, the nearest star to our sun. That's over 4 light years away. A message sent at the speed of light would take more than 4 years to reach them. You take a breath and open your box. You have a special device that measures a property of your photon called polarization. Let's say you measure it to be vertical. At the very instant you do this, not 4 years later, not 4 minutes later, but in the same infinitesimal tick of a clock, the photon in your friend's box, 4 light years away, instantly becomes horizontal. If you had measured yours and found it to be horizontal, theirs would have instantly become vertical. This isn't a magic trick. It's not a theory. This is a fundamental aspect of our reality, proven beyond any doubt. It's called quantum entanglement, and it is arguably the most mysterious, most profound, and most reality-shattering phenomenon ever discovered. Albert Einstein, the man who conceived of the fabric of spacetime, could never accept it. He called it spooky action at a distance. He spent years trying to prove it was a mistake, a sign that our understanding of the universe was incomplete. But as we'll see, the universe is even spookier than Einstein feared. Today, we're going on a journey to the very edge of understanding. We'll explore this ghostly link that connects particles across the cosmos, a link that challenges our ideas of space, time, cause, and effect. We'll see how it's not just a curiosity, but the foundation for a new technological revolution. And we'll ask what it means for us, living in a universe that is far more interconnected than we ever thought possible. So, what is quantum entanglement, really? To get a grip on it, we first have to understand that the quantum world doesn't play by our rules. Down at the level of atoms and particles, things are not solid, definite objects like we see in our everyday lives. They exist in a state of blurry potential, a cloud of possibilities. This is called a superposition. A particle isn't here or there. It's in a superposition of being in both places at once. Its spin isn't up or down. It's in a superposition of both up and down. This cloud of possibilities is described by a mathematical tool called a wave function. The wave function contains all the possible states of a particle, but the moment you try to look at it, the moment you measure it, the superposition collapses. The cloud of possibilities vanishes and the particle is forced to choose a single definite state. Entanglement is what happens when 2 or more particles are created in such a way that they are described by a single wave function. They become one system. They lose their individual identities and merge into a single unified quantum entity, even if they fly apart at nearly the speed of light. Let's try an analogy. Imagine you have a pair of special quantum coins. They haven't been tossed yet. They don't have a heads side or a tails side. They are blank. Their state is undefined. You give one to Alice and send the other to Bob on the far side of the galaxy. Alice decides to look at her coin. The moment she observes it, the blank disk is forced to choose a state. Let's say it becomes heads. Instantly, across the galaxy, Bob's coin, which was also blank and undefined, becomes tails. The act of Alice observing her coin created the reality for both of them. This is the crucial difference from our everyday intuition. It's not that the coins were secretly heads and tails all along. It's that neither had a defined state. The reality of heads or tails did not exist anywhere in the universe until the moment of measurement, and when it was created in one place, it was simultaneously created in another, no matter the distance. The particles are linked by a shared state of being, a single story being told across 2 points in spacetime. This idea was so bizarre, so contrary to all of physical intuition, that it sparked one of the greatest debates in the history of science. On one side was Albert Einstein. For him, reality was something solid, objective, and local. An event happening here should not instantaneously affect something over there. This was the principle of local realism. In 1935, Einstein and his colleagues, Podolsky and Rosen, wrote a paper that became known as the EPR paradox. They argued that if quantum mechanics was true, the world would have to be a very spooky place. Their argument was a direct challenge to the new physics. They said, look, if Alice can measure her particle and know with 100% certainty the state of Bob's particle, without ever touching or interfering with Bob's particle, then the state of Bob's particle must have been real all along. To Einstein, the alternative, that Alice's measurement somehow reached across space and created Bob's reality, was unthinkable. He concluded that quantum mechanics must be incomplete. There had to be some missing information, some hidden variables or secret instruction sets within the particles that determined their states from the moment they were created. The universe, in his view, was not playing dice. There was an underlying deterministic reality we just couldn't see yet. On the other side of this great debate was the Danish physicist Niels Bohr, one of the founding fathers of quantum theory. Bohr's reply was profound. He argued that Einstein was asking the wrong questions. The role of physics, Bohr said, is not to discover what nature is, but to describe what we can say about nature through observation and measurement. According to Bohr's Copenhagen interpretation, it's meaningless to talk about the properties of a particle, like its spin or position, before it's measured. There are no hidden variables. There is no pre-existing reality to uncover. The wave function isn't a picture of a real particle. It's a complete catalog of the probabilities of what we might find if we choose to look. The universe, at its heart, is fundamentally uncertain, and reality is only brought into focus by the act of interacting with it. For decades, this remained a philosophical standoff. It was a debate about the very nature of existence, with two of the world's greatest intellects on opposing sides. It seemed impossible to resolve. How could you ever test what was real versus what was created by measurement? The stalemate was finally broken in the 1960s by a physicist from Northern Ireland named John Stuart Bell. Bell was fascinated by the EPR paradox and wanted to see if it could be moved from the realm of philosophy into the laboratory. He devised a brilliant piece of mathematics now known as Bell's theorem. Bell's theorem is a masterpiece of logic. He imagined what would happen if Einstein was right, if there were local hidden variables that determined the outcomes of quantum measurements. He created a mathematical inequality, a rule that any such common-sense theory must follow. Think of it like this. Imagine you're testing thousands of pairs of entangled particles by measuring their spin along different axes or directions. If each particle has a pre-existing instruction set, a hidden variable, there's a statistical limit to how strongly their results can be correlated when you measure them along different angles. It's just a matter of basic probability. Bell's inequality sets a hard limit on that correlation. But then, Bell calculated what quantum mechanics would predict for the same experiment, and he found that quantum mechanics predicted correlations that were stronger than the limit allowed by Einstein's worldview. The correlations were so strong they could not be explained by any pre-existing information. They could only be explained by a genuine, non-local connection. Bell had transformed the debate. He had given physicists a clear, testable prediction. Either the correlations between entangled particles would obey his inequality, and Einstein was right, or they would violate it, and the universe was as spooky as Niels Bohr claimed. The challenge was laid down. All that was left was to perform the experiment. In the early 1980s, a team led by French physicist Alain Aspect at the University of Paris-Sud took up the challenge. They designed an ingenious experiment. They generated pairs of entangled photons and sent them in opposite directions down long tubes. At the end of each tube was a detector with a polarizer. Here was the crucial part. The setting of each polarizer, the angle at which it would measure the photon, was changed incredibly fast in just a few nanoseconds, while the photons were in flight. The choice of measurement was made so late that there was no time for any signal, even one traveling at the speed of light, to pass between the two photons or from the detectors back to the source. This closed a major loophole, ensuring the particles couldn't have some secret, prearranged agreement. The world of physics held its breath. The results came in, and they were decisive. Bell's inequality was violated by exactly the amount predicted by quantum mechanics. Einstein, for all his genius, was wrong. There are no hidden variables. The connection is real, it is instantaneous, and it is fundamental to the fabric of our universe. Since Aspect's experiment, dozens of others have been performed, each more precise than the last, closing every conceivable loophole. The verdict is in. Reality is non-local. But the weirdness doesn't stop there. This connection between measurement and reality leads to some truly mind-bending conclusions, best illustrated by the famous double-slit experiment. When you fire single particles, like electrons, at a barrier with two thin slits in it. They don't behave like tiny baseballs. They behave like waves. Each particle seems to pass through both slits at the same time, interfere with itself, and create a distinctive interference pattern on a detector screen behind the barrier. This pattern is the smoking gun of wave-like behavior. But here's the quantum twist. If you place a detector by the slits to see which slit each electron actually goes through, the interference pattern completely disappears. The electrons stop acting like waves and start acting like simple particles, going through one slit or the other. The very act of observing their path forces them to abandon their wave-like nature and choose a definite route. It's as if the universe behaves differently when it knows it's being watched. Now let's connect this back to entanglement with the quantum eraser experiment. In this setup, we entangle two particles. Particle A is sent through the double slits. Particle B, its twin, is sent to a distant detector. By measuring particle B in a certain way, we can learn which path its twin, particle A, took. And just as before, as soon as we gain this which path information, the interference pattern for particle A vanishes. The entanglement allows us to observe the path without ever placing a detector at the slits themselves. But here is the part that twists our notions of time and causality. The experiment can be designed so that the decision to measure or erase the which path information for particle B happens after particle A has already hit the detector screen. If we later choose to look at particle B's data and determine the path, the interference pattern for A is gone. But if we choose to perform a different measurement on B, one that erases the which path information, the interference pattern for particle A reappears from the data. Think about what this implies. An action you take in the present seems to be affecting an event that has already happened in the past. It suggests that reality is not a story written in indelible ink, but a fluid narrative that is not finalized until all the information about it has been settled. So, if this connection is real and instantaneous, does that mean we can send messages faster than light? Can Alice and Bob use their entangled particles to have an instant conversation across the galaxy, violating Einstein's cosmic speed limit? The answer, perhaps surprisingly, is no, and the reason is subtle but beautiful. While Alice's measurement instantly determines the state of Bob's particle, Alice has absolutely no control over the outcome of her measurement. When she measures the spin of her particle, she has a 50-50 chance of getting up or down. The result is fundamentally random. From Bob's perspective, on his distant world, all he sees is a random sequence of ups and downs as he measures his particles. His data looks completely random. It's only later, when Alice calls him on a classical communication channel, like a radio, limited by the speed of light, and says, "Here's my sequence, up, down, down, up," that Bob can compare it to his sequence, down, up, down, and see the perfect, instantaneous anti-correlation. The correlation is instantaneous, but information transfer is not. You cannot use entanglement to send a deliberate message. This is known as the no-communication theorem, and it keeps entanglement from breaking the laws of relativity. The universe is spooky, but it's not illegal. This might seem like a strange quirk of nature, but it's a quirk that is powering a new technological revolution. The most famous application is quantum computing. Your laptop works with bits, which are either a 0 or a 1. A quantum computer uses qubits. Because of superposition, a qubit can be a 0, a 1, or both at the same time. By entangling these qubits, their power explodes exponentially. A few hundred entangled qubits can process more information simultaneously than there are atoms in the known universe. These machines promise to revolutionize medicine by simulating molecules to design new drugs, create new materials for hyper-efficient batteries, and solve complex optimization problems that are impossible for even the biggest supercomputers today. Then there is quantum cryptography. Entanglement offers a way to create perfectly secure communication. If Alice and Bob want to share a secret key for encryption, they can do it by measuring entangled photons. If an eavesdropper, Eve, tries to intercept the photons to learn the key, the very act of her measurement will disturb the delicate entanglement. This disturbance instantly alerts Alice and Bob that their channel is being watched. Security is guaranteed not by a clever algorithm, but by the fundamental laws of physics. We are also learning to build quantum sensors of incredible precision. By taking advantage of entanglement, we can create devices that can detect tiny fluctuations in magnetic fields, which could lead to new ways of imaging the human brain, or even detect gravitational waves with greater sensitivity. Beyond the technology, entanglement forces us to confront the deepest questions about the nature of reality. What is the universe really made of? A breathtaking idea on the frontiers of theoretical physics is a conjecture called EPR. It proposes that the spooky connection of entanglement, EPR, is geometrically the same thing as an Einstein-Rosen bridge, better known as a wormhole, ER. This radical idea suggests that two entangled particles are literally connected by a microscopic tunnel through spacetime. If this is true, it means that entanglement isn't just a strange phenomenon that happens within space. It may be the very thing that creates space. The universe's vast, three-dimensional geometry may be an emergent property, stitched together by an infinitely complex network of quantum entanglements. In this view, space itself is a hologram projected from the information contained in these quantum connections. This scientific discovery resonates with some of the oldest philosophical and spiritual ideas of humanity, the concept of an underlying unity to all things. The notion that separation is an illusion. Quantum entanglement challenges our most basic assumptions: that things are separate, that space is empty, that the future cannot affect the past. It reveals a universe that is not a collection of isolated objects, but a single, indivisible whole. A vast, interconnected system where a measurement on a particle in your hand can have consequences on the other side of the galaxy. You, me, the Earth beneath our feet, and the most distant stars in the night sky. We might all be connected in ways far more literal than metaphorical. We are all part of this spooky, mysterious, and deeply interconnected cosmos. And as we continue to explore these ghostly links, we are not just learning about the universe, we are learning about the very nature of our own reality.